Hi, recalling previous video, let's give a start to new one. We were talking about alternating series. By an alternating series, we mean a series whose the signs of terms change successively, and for such a series, we have a useful test called Leibniz test, and this test works in such a way that if the positive part of an alternating series holds these two conditions, then it's convergent, otherwise it's divergent. So let's recall these conditions. The positive part must be decreasing, and its limit, of course, infinite limit, must be zero. Let's investigate an example. This is an alternating series, because we may understand from this part, and the positive part is 1 over k. It's clearly this part is decreasing, and you can see from this line. For any k belongs to the natural numbers, you have this inequality. This means that ak always greater than ak plus 1. So this means that the first condition of Leibniz test satisfies. For the second one, which is easy, because the positive part is 1 over k and its limit clearly 0. So both conditions hold, and this means that your alternating series is convergent. Another example. Okay, we have an alternating series. We understand from this part, and the positive part here is ak. Okay, and ak, we first of all, such an ak, it's clearly is a rational function, which means that and this part and the denominator is a polynomial. So, and their degrees are equal. That's why the limit is the ratio of the leading coefficients. We can see that. It means that this limit is equal to 1. Is not 0. Then we can say that Leibniz test doesn't, the conditions of Leibniz test do not hold. That's why you can say that the given series is divergent. And also, the terms of positive parts is also increasing. Neither of conditions of Leibniz test do not hold. That's why such an alternating series is divergent. Let's have a look at another example. This is also an alternating series because of the properties of the trigonometric function cosine. As you can see from this line, the signs of the terms change successively. So indeed we have such an alternating series, and for the positive part equals to 1 over k factorial, and it's clearly the terms are decreasing, and also obviously this limit is equal to 0, which means that the conditions of Leibniz tests hold, and that's why the given series is convergent. Well, and okay, we can launch another part for the section of series. As you remember, we have three kind of series. The first one is the positive series. The second one, alternating series. And the third one, power series. Okay. First, introduce a power series. Just a minute. Okay. Yeah. Just to recall, I wrote it. Okay, a power series is a function of x. Is a function of x in the form, and here is x is a variable, and ck are constants, and also a is a fixed number. So, and by a power series, we know we have to know and this format. Okay, until now we have known some series, we have seen some series in which any variable does not exist, but from now on we have some series including some variables like x. Okay, an example of power series, for instance, for such a power series, ck 1 over 3 power k, and the a is 0. Okay. For a power series, we have 3 points. The first one is to determine the value of a, called center of convergence. Okay, from now on we call the constant a center of convergence. And the second point is to find the radius of convergence, r. Okay, and the last point is to find an interval of convergence I. So let's formally define those notions. Consider the power series, this one, the interval, and the interval of convergence is an interval in which the given series is convergent, and we denote this interval by I. Okay, the radius of convergence and half length of interval of convergence I is called radius of convergence, and we denote it by R, capital R. Okay. For such a power series, A is center of convergence, and R, please pay attention this formula, this equality. This is the formulation of the radius of convergence, and the interval we may find interval x the absolute value of x minus a and smaller than r. Okay, we use this formula to find an interval of convergence, and this is the formula for the radius of convergence. Okay, so this note is important for a power series, and the series is all time convergent at the point x equal to a, which means that a power series is always convergence at its center, and the series can be convergent for all x, and the series can be convergent only the special values of the x. Okay, this one happens, this item, this property or this possibility happens, and provided r equals to infinity. So if you find r equals to infinity, this means that your power series is convergent for all x. And if you this possibility happens provided r equals to 0. If you find r equals to 0, this means that your power series is convergent only at its center. Otherwise, namely, if your radius of convergence is neither 0 nor infinity, then you have this possibility, which means that you have an interval of convergence and some special values of x, your power series is convergent. So we can see in this diagram, okay, as you have center and you have an r, finite r, and this interval, okay, is the one of convergence. Okay, we have useful tests, is a unique test for power series, Cauchy-Hadamard tests. For a given power series, the series is convergent, this interval, and the series is divergent for this condition. By the way, the Cauchy-Hadamard theorem or Cauchy-Hadamard tests works, and the inside points of the interval of convergence, and also Cauchy-Hadamard theorem works also at these points, but this test doesn't work at the end points. So we have to observe also the end points at the end points of the interval. Well, this is the note, what I am trying to say. Cauchy-Hadamard test doesn't say anything. What happens at the end points of intervals? Say a plus or minus r. And in general, the power series is convergent or divergent at endpoints. Okay, so let's give an example. Find the radius of reduce an interval of convergence of this power series. Okay. First, determine the center. The center clearly 3, and the constant part ck equals to 1 over k multiplied to power k. So we have to compute this limit. Okay. After some manipulations, we have this limit, and this limit equals to 2, which means that our radius of interval 2, okay, the radius 2. Those calculations are simple. Okay, we have the center equals to 3 and the radius are 2, so that's why our interval, as can be seen from this inequality, our interval is an open interval 1,5. So our Cauchy-Hadamard theorem says that inside points in given series is convergent, and exterior points, at exterior points, the power series is divergent. So we have to observe at the endpoints. For instance, we have to look what happens at the point x equals to 1. If we replace x with 1, then we obtain an alternating series, as can be seen here, or after some eliminations we have this alternating series, and we know very well this is convergent. So this means that at the beginning, Cauchy-Hadamard theorem says this is an open interval, but we calculate that the power series is also convergent at the point x equals to 1. So we have to close this interval from the left part. Okay, and let's see what's happening at the point 5. So if we replace with x with 5, then we obtain such an harmonic series. By the way, we substitute 5 in this power series. Okay. So we have an harmonic series or P series. So from the test of harmonic series, this is divergent. So which means that our interval of convergence 1,5, the semi open interval. Okay, this one. This is the solution. Okay. So here is belongs to the interval, but the 5 doesn't belong. Another example. Find the radius and interval of convergence for the given power series. As can be seen, the center of convergence is equal to 0, and the constant part 1 over k factorial. So for the radius of convergence, after some manipulations, we use the properties of the factorial. we find this limit, which is clearly infinity, which means that our radius is infinity. Then our interval is the real axis, this one. Okay, which means that at the all points of the real axis, our power series is convergence. Yes, this one is such an power series is convergent at each point of real axis. Okay, another example in which we have to find the radius and an interval of the power convergence for such an power series. As can be seen, the center of the power series is equals to -2, and the constant part k factorial. So, and by using the properties of the factorial, we may find easily r equals to 0, which means that the given power series is convergent only at the point x equals to -2. Namely, it's convergent only at its center. Okay. So we may start a subsection called Taylor's series expansion. Okay, let's start by its definition. Suppose that f is a differentiable function of any order in the neighborhood of a point A, then this power series, okay, this power series called Taylor series expansion of f of x about x equal to a. So the Taylor series expansion is the second aim of why we teach the topic of series, because via Taylor series expansion we may write any function in terms of a polynomial whose many infinity terms. So that's why it's very important topic in mathematics. Well, let's have a look into the equality one. I mean the Taylor's expansion formula. As can be seen that this part, I mean the denominator, and is independent from the function of f of x, and here also is independent from the function f of x. Only this part is dependent of the given function. So, which means that here is, by the way, the a will be given in problems. So, only part we have to find these derivatives. What I am trying to say, this is a formula of a part, a constant part. Here is also, and the value of a will be given in problems. Only we have to find the only part we have to find these derivatives. Okay. In this note, we say that f of x power k, we mean the kth order the derivative, higher order derivative. Yes, this one. To find Taylor series expansion of a function, the first we have to find this higher order derivative at its this value, and then we replace with the values of the derivatives with this formula in equality 1, and then it's over. And Maclaurin series is a special case of the Taylor series expansion. If your values equals to 0, by the way, here is a equal to 0, then your series expansion is called Maclaurin series expansion. Okay. You may use the both notions. I mean, you can say Taylor series or Maclaurin series. It doesn't matter. We have an example. Find the Taylor series expansion of the function f of x equals to e power x about x equals to 0. So, as we pointed here in blue, we have to find higher order derivatives at the point x equals to 0. As you can see, here is same, here is same, and the 0 was given in the problem. Only part we have to find the higher orders derivatives of a given function in the problem. Okay, let's find the derivatives. It's clearly all are the same, and the values of the function e power x at 0 equals to 1. So, which means that we have to write 1 exactly here. Then we have such a power series, which means that you have an exponential function. And you can write it as a polynomial with infinitely many terms. This is the point. Okay, and this note is important. Let's obtain the Taylor series expansion of the irrational number e, and we have this equality already. We found it. If we replace x with 1, then you obtain this power series. Sorry, this is a positive series, which means that you can write an irrational number and like a positive series. Yes, this is approximately 2.71. Okay, and another example to find a Taylor series expansion of a function, a rational function 1 over x about x equals to 1. So this means that a equals to 1. So here is same, here is same. Then we have to find the higher order derivatives of 1 over x at x equals to 1. Okay. We have to use the properties of derivatives. Yes. you can write f of x like x power minus 1, and the first order derivative, and the second order derivative, and the third order derivative. Those are simple derivatives. And as you can see, there is a simple relation between among those derivatives. Yeah. Processing these derivatives, you can easily find the k order derivative equals to minus 1 over k power k factorial multiply x power minus k plus 1. This is the formula of any order derivative of the function f. So if you put 1 into this equality, this equality, we have to put 1 because our point is 1. Then we obtain minus over k multiply k factorial. If we replace this value, this, with this statement, then we obtain such a power series, which is the Taylor expansion of the function f of x equals to 1 over x. Another example to find Taylor series expansion of the function logarithm x at the point x equals to 1. Okay. As you can see, here is same. This value already was given in the problem. The only part we have to find those derivatives. So we have a simple function. F of x equals to logarithm x. The first order derivative 1 over x. The second order derivative minus 1 multiply x power minus 2. So those are the simple derivatives. If you continue these processes, these higher derivatives, you can find the any order derivative, say k, equals to minus 1 over k minus 1, k minus 1 factorial x power minus k. So we have to replace x with 1, then we obtain such a statement. So finally, we have to replace this value with the derivatives. Then we find here is k, such a power series. This means that around x equals to 1, you may write logarithm x. You may write logarithm x around x equals to 1. This is the logarithm x. So another example. Let's find the Maclaurin series. Is the function a power x. Because of the Maclaurin series, we have to take here is 0. By the way, I is a positive real number and different than 1. So we have to find higher order derivatives. Okay, it's a power function. And if we use its derivative properties, the first order derivative, a power x multiply logarithm a and logarithm a square and logarithm a power 3. So processing the same properties, we may find the k order derivative equals to a power x logarithm a power k. So this is the problem requests from us that to find the Maclaurin series expansion. So we have to put here 0, then we find logarithm a power k. So finally we have this equality. Okay. By this example, we may end this video.